Right. Thank you. And I'd like to thank the organizers again. This has been a very interesting meeting. I'm learning a lot. So I want to talk today about a particular example I gave during my lectures a few days ago. This is based on some work with Gökçe, Bazar, and Mithat Unsal. So just to review, one of the aspects of resurgence that I think is particularly interesting to physicists is the possibility that fluctuations around different critical points or saddle points are somehow related. In a sense, I think that's the main message. It's not guaranteed that it's always related, but it's something new to look for. And there's a surprising number of examples so far where it is true. Which is what you would need to actually justify some sort of decomposition like this in terms of thimbles and saddles. But I want to distinguish between two completely different types of resurgent relations like this. One is what I would call generic resurgence. These go by the name of low-order, high-order relations. And this you can see from the example I gave in my lectures from a result of Michael Berry and Chris Howells, that if you just take an ordinary contour integral with some function in the exponent that has multiple critical points, so points where the derivative is 0, and this is the steepest descent contour through critical point number n, this can be expanded with the usual exponential factor and Gaussian prefactor, but then an entire series of all of the other terms. So there's a generic fact that the large order growth of these coefficients, so R is the index of the order of the coefficients in this expansion, and n labels the critical point, they grow factorially with R, and the leading overall multiplicative factor is the 0th order fluctuation factor from, so if we're expanding here, from neighboring critical points. And the subleading corrections are the first, second coefficients in the fluctuations around this critical point. So you're relating the large order growth of the coefficients around this point to the low orders of neighboring points. Okay, so I call this large order, low order, and this is completely generic for contour integrals. And I really urge you to just go play with an example. It's really illustrative and very easy. So it's satisfying. It's something you can do quickly and you feel like you learned something. And this also holds in many examples in path integrals. And if we're ever going to make sense of this type of formula, this structure should be there somehow. Okay? So that's what I would call generic resurgence. There are many, many cases. What I want to talk about today is a much more specific case, which I call constructive resurgence. There are certain examples, and I want to characterize them completely now, where even the low orders are related. Okay, so I'll explain in great detail as we go along, but this is relations between the low orders of fluctuations in one point and the low orders at some other point. In particular, I call it constructive because it means I'm going to tell you about examples where if you give me 10 terms and the fluctuations there, and now do a quantum mechanics problem, so there are an infinite number of critical points, but you give me 10 terms of the fluctuations around the vacuum saddle, I can give you 10 terms of the fluctuations around every other saddle. Okay, so it sounds just impossible, ridiculous, absurd, but I'll show you how it works and why it works. Okay, so this is a really extreme form of resurgence. It doesn't always hold. The generic one, I would say, always holds. This one's very special, but there are many examples. Okay, and the sort of starting point is that the splitting around the one instanton, the fluctuations around the one instanton, can be completely characterized in terms of the perturbative fluctuation. But I stress that it holds throughout all other instanton sectors as well. Okay, so there are many examples of this. If you look back in hindsight, you can see traces of this in various calculations in quantum chemistry, in solid-state physics, in laser physics. Some beautiful old work by Gabriel Alvarez and his student Cazares in some oscillators. And then we found all sorts of examples And I'd also stress that there's some overlap, at least in spirit, with what Ricardo was talking about yesterday with in string theory, where you've got free energies that are functions of, say, a coupling and also an n. That's exactly the structure that appears here. Okay, so I'm going to start off very specifically and talk again about this periodic potential, the cosine potential. And here's a picture of the spectrum. There are bands, there are gaps. There's a function of coupling, and here's the energy. I switched notation again. This is supposed to be the energy. So you see that the potential goes between -1 and 1. It's a periodic potential. So deep down, they're harmonic wells. So the energies are n plus a half times h bar. Okay? So these are just different slopes times h bar. As you go up, the bands widen. As you cross the top of the potential, the bands are no longer exponentially narrow. They become more or less continuous. And up here, you have very narrow gaps. Okay? So this is a very intricate structure in this spectrum. And so the sort of textbook answer is you do perturbation theory. Perturbation theory more or less gives you the center of these narrow bands. Okay? There's splitting around the bands, and the splitting is, of course, an exponential instanton factor with a prefactor, and this much we all know how to do. What I'm saying is that the fluctuations around that one instanton is also a perturbative series. It's also asymptotic, but here's an exact formula for it in terms of the perturbative sector. Okay? And all these dots, the 2 instanton, 3 instanton, I can write a corresponding formula all in terms of this. Okay? So it just seems impossible. And, you know, unfortunately, I'm being recorded, but I should confess that Mithad and I set out to disprove that this could never happen. And to our horror, we found that it does happen. There's a similar formula. I write this formula here for the bands, but there's an analogous formula for the gaps also. It's true everywhere in the spectrum. So this begs a question. Why is it happening, and when does it happen, and how does it happen? I'm going to borrow some terminology from Seiberg-Witten and the Nekrasov-Shattashvili results, because I'm not just doing this as an exercise in quantum mechanics. There are deep relations to quantum field theory and an integrability here. And we're going to just basically combine some of that machinery and terminology with really just basic WKB, and something quite interesting comes out. So let's go back and just do a bit of classical mechanics. So in one-dimensional classical mechanics, here's the energy, kinetic potential. I'm going to rewrite this. This is the most complicated part of the talk. I'm going to rewrite this as p squared as some constant minus the potential. So if this as a function of x is quartic or less, after doing changes of variables possibly, then this defines a torus. This is a genus 1 elliptic curve is the fancy terminology, but if you're not familiar with that, don't worry too much. So here's a picture of a torus. The important thing about a torus is that there are 2 independent cycles. And classical mechanics says here's the action, which is the integral around one of these cycles of the square root of E minus V. Classical mechanics. And the period of that motion is the derivative with respect to E of the action. Okay, so think of, sorry, chalk. Okay, colored chalk. So I can rattle back and forth in one of the wells, and this is the action for that motion, and this is the period. Or I can also go through the barrier, and that's the dual action and the dual period. Okay? And it's a torus. There's one of each. So just some classical geometry. These can all be written in terms of elliptic functions. That's why the elliptic functions were invented in the first place. Exactly this problem in classical mechanics. And so there are 3 of those. They satisfy, the periods satisfy a second-order differential equation. The actions satisfy a third-order equation, which has a fancy name, the Picard-Fuchs equation, with respect to energy. Okay, so this is classical geometry from classical mechanics. Now, what about quantum? So here's all orders WKB. There's this beautiful old paper by Dunne from 1932. You can expand the action in a series in h bar squared, and each coefficient is some function of energy. The 0th order one is just the classical action and the classical dual action. And so here's the classical one, and we've all done these at some point. We know that they become horribly messy, but there's a formal way to expand this. There's a recursive structure for generating all these integrals. And this is the action, and this is the dual action. Okay? Now notice that the integrands are identical. This is really important. I mean, it's trivial, but it's important. The only thing that's different is whether you're going around this cycle or that cycle. Okay? So what all orders WKB or exact WKB says is that if you know these two guys to all orders in h bar, you know everything about that quantum mechanics and that quantum mechanics, you know that you've solved the problem. You can plug them into some boundary condition, which is an exact quantization condition. You have some transcendental solution of the entire problem. Okay, so what I'm going to do now is give you a very simple argument, which is that if I know this, I automatically know this. Okay? And that then proves that this, I'll explain why this is perturbative information, encodes all of the non-perturbative information. Remember, the dual is related to the going around, rattling through the barrier, and the other one is classical motion inside a well. Okay? So, step one. The proof is sort of invoking the gods, right? So we can't argue with Riemann, right? So classical geometry says that knowing the classical period determines the other one. Basically, it's Stokes' theorem. I'm quoting another god, right? Which is that it's a torus, so you just integrate all the way around, and so one of the loops is expressed in terms of the other loop. Okay? I'll show you explicitly in examples how it works, but that's where it comes from. So that's the starting point. Classically, if I know one of the actions, I automatically know the other one. Okay, here's something that's not immediately obvious, but if I calculate this to all orders in h bar, this action, I now have some expansion in powers of h bar squared. All of the coefficients are functions of energy, and that's set equal to some integer plus a half. Okay, for bands. If you invert this and write energy as an expansion in h bar with coefficients that are functions of n, that's exactly perturbation theory. Okay? Now, you may not have thought of it this way because we sort of lie to our students and tell them that WKB tells you information high up in the spectrum. It's not true. It tells you information everywhere in the spectrum. Okay, so it turns out this is actually a very efficient way to do high-order perturbation theory. Okay, so that's why I call A the all orders WKB inside the well, not in the barrier, but in the well. That's why I call it perturbation theory, because it's just an inversion of perturbation theory, the information for perturbation theory. Okay, so we're almost done. We have to invoke some other gods. Is that all of these weird integrals can be expressed in terms of elliptic functions. They're actually algorithms that you can program to take these things and just integrate by parts and shuffle things around to rewrite them in terms of this and derivatives of this with respect to energy. You see that if you differentiate with respect to energy, you just get 1 over that square root, but then because V satisfies, it's a genus 1, you can shuffle around V and rewrite it in terms of the starting action and derivatives acting on the starting action. Okay? Now, okay, yes?
Is it possible to make this word dual a little more obvious to
what? Dual?
The outside and the tunneling dual to each other. How do you see that as a dual?
It's just a name. I'm borrowing the name.
It doesn't mean anything.
Well, it's the dual cycle, so it's just terminology. It is dual in that sense. You'll see in a minute. Okay. Okay. So nth order in that expansion in powers of h bar squared can be gotten as an nth, or n plus 1th or something, differential operator acting on the classical action. Now comes the important point that these integrands are the same. Because in fact, that statement is just a statement about manipulating the integrands. Because I'm doing closed loop integrals because I manipulate the integrands and I can take those differential operators outside of the integration argument. And so if I can manipulate this guy, I can manipulate this guy, and it's exactly the same manipulation. So what that means is that in the expansion of the dual action, it's exactly the same differential operators, but acting on a different starting point. Okay. People are looking stunned, but okay. The point is, these operators are identical, but they're acting on a different starting point. But now we're finished because knowing this means I know this by point 1. And if I know perturbation theory to some order, that means I know these differential operators to some order. And if I know those differential operators to some order, I can immediately calculate this to the same order. So I'm finished. Okay. If I know the action, the WKB, all orders to order 37, I can simply write down the dual action to the same order. Okay. Just write it down. So in this really weird way, not doing perturbation theory the way you normally do it, but doing it in this semi-classical way, tells you that perturbation theory encodes all of this non-perturbative information in a non-obvious way from the point of view of usual Feynman diagram type expansion, but in a very natural way in the sort of semi-classical language. Okay, so that's a little abstract. I think it's nice to see that it's guaranteed to work. So let's now look at some examples and just see how it actually works in practice. So you could even ask a more refined, this just tells you that there's some relation between the non-perturbative stuff and the perturbative stuff. But now we can ask a more specific question. I wrote a very concrete formula for the relation between perturbative information and non-perturbative information. So we can ask, for which potentials is there a formula like that? Okay, so we started with a guess, which is these Chebyshev potentials. And so Chebyshev polynomial squared is the potential. So if m is an integer, it just generalizes this double well. So triple well, can't even see how many that is, 4, 5, whatever, okay? So there's a really interesting thing about these potentials, even classically. Imagine you calculate the action for motion in this well as a function of energy and the period. And then you go do it in this well. Well, this well is different from this well. And this well is different from this well. Here they're the same, but here they're different. Okay? It turns out that the action and the period as functions of energy are identical in every well, up to an overall factor, constant, which is just the ratio of the two frequencies. Okay? It's amazing. Okay? And there's a geometrical reason for that, but I was kind of, that's going to be a homework question next time I teach classical mechanics. It's really kind of amazing that the oscillation period and the action are identical up to an overall factor. So what that means is these potentials, even though as I increase m, there are lots and lots of wells and lots of different barriers, classically, there's only one action and only one dual action. Okay, so these are good candidates for maybe some of this structure generalizing the double well structure. And if m is infinity scaled appropriately, this is the periodic potential also. And if m is a half integer, then you get these sort of odd ones, which of course are going to be metastable, but these generalize this cubic oscillator. And again, there's only one actual action function and only one dual action function. So even though this doesn't look anything like a genus 1 system, classically it behaves as if it is. Okay, now a little bit more detail. here's the action and the dual action, proportional. There's some overall constant depending on which well I'm talking about or which barrier, but they're just hypergeometric functions where m is the Chebyshev index. They satisfy some second-order equation. Because it's a second-order equation without a first derivative term, there's a very simple Wronskian relation. So there's a relation between remember that the period is the derivative of the action with respect to energy. So this is the Wronskian relation. If I rewrite this, invert it, I get what people in the sort of Seiberg-Witten world call the Mittoni relation at the classical level. It's just the Wronskian relation for this hypergeometric equation. You can do something a little bit more fancy, again motivated by, this is coming to Richard's question, motivated by the Seiberg-Witten machinery. You can define a modular parameter, which is the ratio of the dual period and the period. And in terms of that guy, not in terms of energy, but in terms of that guy tau, the action is just the derivative with respect to tau 1 over frequency, and the dual one is just the derivative with respect to the dual guy is just the inverse of this with a minus sign flip. And I can rewrite the Wronskian relation in this language to show here that once I know A0, I just differentiate to work out omega 0, and then tau 0, remember the dual guy is related to the other guy just by changing E to 1 minus E. So once I know this, I can reconstruct the dual one. So that's the explicit form of what I said before, that from Riemann, that once you know A0, you immediately write down A0 dual. You don't have to do any more integrals. So now that was at the classical level. These are kind of interesting potentials for classical mechanics, but what about when I quantize? So we end up with something that takes this geometry, this Riemann geometry, we're going to deform it with H bar, and we're going to discover that it doesn't deform very much. And that's what we'll call quantum geometry. And this has relations to all sorts of fancy stuff, mirror symmetry, Calabi-Yau manifolds, quantum modular forms, and there's some interesting number theory. So it's actually a great honor and pleasure to be giving this lecture in the Ramanujan lecture hall, because now I'm going to talk about Ramanujan. So remember that I said that these elliptic integrals were basically invented for the cosine potential problem. So here's the hypergeometric expressions, but I can write them in terms of E and K. And the Wronskian condition for this problem, remember they satisfied a second order hypergeometric equation, so there was some Wronskian relation. That's just what's called the Legendre identity for these guys. And all of this is sort of buried in these old ancient math books, but resurfaced in the guise of Seiberg-Witten theory. Now Ramanujan, for reasons that nobody knows, was trying to generalize this. Oh, sorry, one more thing. What's special about this system is that, remember I defined tau 0 as a ratio. I put in a factor here just to be consistent with what I'm going to say next. The point is you can invert this. One of these magic things about modular symmetry and number theory, you can invert this relation and write the energy as a function of tau 0. It's extremely non-obvious that you can do that. And then, since the period and the action were functions of energy, I can write them as functions of tau 0, and they turn out to be nice simple functions of tau 0 also. So there's all sorts of number theory going on here. And S-duality and T-dualities are just these actions, so it really is a duality, Rich. So in the sense you were probably thinking of. So now Ramanujan was trying to generalize this, and he noticed that if you take these elliptic functions, which are F21s with a half and a half, and replace it with 1 over some integer and 1 minus 1 over some integer, where m was one of those 4 integers, all of the structure of modular stuff generalized. Okay? Now, with just some different constant here. Now, I don't know if you remember, but these are the actions and periods of those Chebyshev potentials. Some of them. Moreover, if you define a modular tau parameter as a ratio of the dual and other period with a carefully chosen factor, R, this actually defines all this modular stuff, just like for the periodic potential. But this, it's interesting, this capital M is related to the little m in the Chebyshev index by this way, but this R here is related to these guys this way, and only for those values of m is R also an integer. Okay, so this is what Ramanujan was doing, and the modular group generalizes in these cases. And there's this beautiful quote from Bruce Bernst's book of Ramanujan. He was expanding these things into these series, and it turns out he was doing all orders WKB for actually the classical version of these for several of these Chebyshev potentials, even though we didn't know why. But later, Bernd actually realized why, because for exactly these values, you can do the same inversion stuff. You can write the energy as a function of this tau zero, and you can write the actions and the periods also as a function of tau zero. And these are the only values that it's possible to do this. Okay? Again, nobody knows why Ramanujan came up with this, but it's since, fairly recently, these things have been proven by number theorists. Okay, so here's a table with these special values, and here's the corresponding Chebyshev potentials. These are the only cases classically for which this modular stuff still holds, generalizing the potential. Now, why on earth am I telling you this, apart from the fact that it's kind of curious and we're in the Ramanujan lecture theater? So these are what the potentials look like. Let's talk now about quantization, and remember this type of relation that came in the cosine potential. So remember, these were the cases where I could write just an absolute simple closed formula for the non-perturbative stuff in terms of the perturbative stuff. So if you rewrite things in the Seiberg-Witten type language, the Wronskian relation was the stuff without the red business. This was just the Wronskian coming from the hypergeometric equation. The amazing thing is, if you now quantize to all orders in H bar, so that E becomes an all orders function in H bar, A is an all orders function in H bar, the only thing that changes is you add this term. Okay? To all orders in H bar. And if you rewrite this as the Wronskian relation, the only thing that you do is you add this H bar d by dH bar of these things that are now all orders in H bar. Okay, so this is the sort of quantum Mattoni version, and this is the quantum Wronskian version of this. So this is the perturbative non-perturbative relation. If you give me the expansion of this guy to some order, I can immediately write the expansion of the other guy to the same order. Now the punchline. The only cases for which that formula holds in the same form are exactly the ones that Ramanujan was studying at the classical level, that preserves this modular structure. And for those four potentials, the formula is identical, just with a different constant on the other side. Okay? So this is completely bizarre, because look at the potentials. They're completely different from one another. Bands, two different wells, two different types of wells, the sort of standard double well. So these are the poster children of instantons. This is metastable, right? Very, very different physics, and yet it's an identical formula. And this new one, the triple well, is kind of interesting because it doesn't look genus 1. And there are some interesting relations to superconformal field theories also. What about other genus 1 systems? I just wrote those ones. Those are the ones for which the relation is of the same form. But remember, I showed you that for all genus 1, there is such a relation. So here are some other pictures. This is the Lame potential. This is an asymmetric double well. This is the double sine Gordon, cosine of x plus something times cosine of 2x. And here's an asymmetric triple well, or non-degenerate triple well. So in all these cases, there's still only one action and one dual action. They're genus 1. Right? So the frequency of oscillation here is the same as the frequency of oscillation here. here, the frequency here is the same as the frequency here, even though they're asymmetric. It's amazing. So in these cases, there is again one of these perturbative, non-perturbative relations. It just looks, it's not just the same form as the other one with a different constant. It's slightly different structure. So what about higher genus, when you've got lots of wells and barriers? So this came up in the lectures the other day. Now you have to deal with hyperelliptic functions, so it's a lot more messy, a lot more complicated. But the conjecture is that to solve this problem completely, you would think that you would have to know to all orders in h-bar the oscillation here, the oscillation here, 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 and the oscillations in the upside down one here, here, and here. So the conjecture is that you only need the real oscillations. You can deduce the barrier stuff from the inside the well stuff to all orders in h-bar from the perturbative data. And, you know, there's some evidence that that's not completely crazy, and I've spoken to some mathematicians who are experts on hyperelliptic functions, and they tell me it's obvious. It's not obvious to me. It would be nice to have some actual calculations, explicit calculations at Genus too. I just haven't had the energy to do it because these hyperelliptic functions are kind of messy and tedious. But I'm fairly confident that something like this holds. And this is pretty amazing if you think about it, that it would say that all the sort of non-perturbative data, these non-perturbative saddle points, the information about these fluctuations is encoded in the perturbative fluctuations around perturbative saddle points. It's really quite remarkable. And behind all of these examples, there's some higher rank group supersymmetric quantum field theory lurking behind them there as well. So I'm over time, sorry. So let me just remind you, there are two types of resurgence. There's the generic one that I now regard as fairly straightforward and not surprising, but there's this much stronger form of resurgence under certain circumstances, and I've given a sort of geometrical approach to why that is true in these cases, and argued that it might be true in other cases. It's also true in supersymmetric quantum mechanics. I didn't talk about that here. It has this weird relation to some of Ramanujan's work in modular functions, and what nowadays would be called quantum modular forms, which is a very active field of research in number theory these days. If you look at this stuff from the perspective of ordinary perturbation theory, they're completely bizarre. Even for the triple well, if you look at this, I'm telling you that perturbation theory in this well is the same as perturbation theory in that well. You can go do perturbation theory, and they don't look anything like one another. But if you do it the other way, you calculate the action here to all orders in h-bar, and the action here to all orders in h-bar, they differ by a factor of 2. When you invert and write the energy as a function of h-bar, as a function of n, that gets completely scrambled. So the coefficients look nothing like one another. Okay? But viewed in this semi-classical language, there's just a factor of 2. It's the same function. Okay? So there are all sorts of weird surprises, even in these simple cases. And then applications to superconformal quantum field theory would be quite interesting. So thank you.
We have time for maybe 1 or 2 quick questions.
I'm just wondering, can you invert the problem and say what potentials have the same action? If I insist that they have the same action, can I derive the potential?
I mean, have the same action?
Same period, I mean.
In each
well.
In each well.
Use that as a constraint on the potential.
Classically. Yeah, I don't know. It may be that the Chebyshev is the answer. I don't know. I'm not sure. Yeah. But you see, at the classical level, all of the Chebyshev were the same. For any index m, a billion, doesn't matter. Okay? So all of its wells. Quantized, it cut off. Okay? There are only these 4 examples. And then somehow that's related to this modular symmetry being important. And that's what's, we see that it works, but why it works is really another question. So to phrase what you're suggesting at the quantum level, I think, is much harder. Okay.
I wanted to know, if one looks at this from differential equation point of view, is the constructive resurgence appearing only if the functions are hypergeometric?
Well, I mean, my conjecture here is it'll hold also for the hyperelliptic. It'll be a different form.
That is right. But if you try to expand these in terms of simple functions, it typically ends up being hypergeometric functions. Let me qualify a little bit. In the sense, the generic resurgence typically has confluent hypergeometric kind of functions.
Generic resurgence holds for any function you want to dream up.
Okay.
I mean, this is true for any differential equation you give me. Linear, nonlinear, I don't care. Okay? There are these low-order, high-order relations. You can give me some random nonlinear differential equation. It's guaranteed. Okay? This is not guaranteed. There's got to be some extra structure here. And I'm claiming that it has something very deep. It's deeply related to this modular symmetry. Because I don't think that's an accident that Ramanujan was playing with these examples.
So you have these results for this energy. Can you say something about the wave functions?
Yeah, because in fact, that energy condition, this sort of Bohr-Sommerfeld condition, is just a monodromy relation for the wave functions.
But one can solve that, and
so I didn't make it explicit, but I assume you can do the same.
so you can use that as a monodromy condition and ask what the functions are.
Yeah. But I haven't done that, but I don't see any obstacle.
Okay. Thanks.
Further questions? So I have a small clarification. Like, you were saying that the action and the dual action were both, like, if you know the action, you know the dual action for all genus 1 elliptic potentials.
Yeah.
So will that hold? So the constructive resurgence holds only for those kind of classical potentials that you were.
No, it holds for a subset of those. Okay? Because that was true for all of these Chebyshev ones at the classical level, but not at the quantum level. So.
Hi. I was wondering about the point on the next slide, actually. Yeah, a unique subclass, identical form of PNP relations.
Yeah, okay, maybe unique is too.
No, what I was trying to get at was the argument involving the differential operators.
Yeah.
That seems to be like I can do that if I write down any quartic potential.
Yeah.
So I was wondering if.
Yeah, but I mean, this is the class where the relation is exactly the same up to a constant.
So
that's what I meant by that comment.
Okay, but the statement that the periods and the dual periods are related to all orders in H bar because they have the same differential operators, that is something that is true for any genus 1 system, right?
Yeah. Yeah.
Okay.
There is a relation for any genus 1 system.
If there are no further questions, then let us thank the speakers and all the speakers for this session, and we'll close the session.